Today I'm going to talk to you about the evolution of the control network for industrial systems, with a particular view of looking at the brownfield, how we solve brownfield solutions. So by way of an introduction, Ethernet to the sensor is coming. So IEEE 802.3CG, or 10Base-T1L, was certified or ratified about 3 weeks ago, and it's going to be delivering seamless Ethernet to the sensor. We expect that to be coming within the next 2 years, so everyone needs to be getting ready for it. So the presentation I'm going to give you will cover the basics of control networks, the evolution of those, and then looking at the impact on brownfield for the future. So starting off with 4 to 20 milliamp current loops. So this is sort of old technology, I guess you call it. So it's been around since the 50s. It's not going to go away for a very long time. It's a very, very large install base. I think I can use this. So where are we? Yeah, here we go. So just walking through the architecture of this. So, the enterprise IT domain talking to your controller, so PLC, DCS. The controller has I/O cards. These are fixed function, so analog input, analog output, possibly some digital here. And then you have 4 to 20 milliamp connections to what's called a marshalling cabinet. And the marshalling cabinet is basically a way of being able to take field signals coming in and routing them to the correct portion of the control cabinet. This is very complex, it's very expensive, it takes a very big footprint. Out to the field, running 4 to 20 milliamp cables, could be several hundred meters, up to a kilometer long. Twisted pair, each sensor has to have a wire going back to the marshalling cabinet. The data rate, very slow. So if you're running HART over these, you're about 1.2 kilobits per second. This wiring, very big, very heavy. It requires conduits, very long cabling runs. And then installation time. You've got a long run here. You've got potential for miswire. You've got a very expensive installation process, and engineer each end of the link, communicating, making sure they've got the right sensor connected to the right I/O terminal. You may have field junction boxes, so talking to a small subset. This could be an extension that you've put on there. So overall, very slow, very complex, but very reliable. It's been around, as I say, for a very long time. So it's rugged. It doesn't suffer from electromagnetic interference too much. It's very robust signaling. It's only 2 wires in the majority of the cases. Changes to the load impedance on this doesn't really greatly affect the signaling. It has a live zero, so that if a cable breaks, you know it's broken, which is good. We can provide loop power to the sensor, so as long as the sensor's not a heavy drain, so a flow meter probably not right, a valve actuator probably not right, but for temperature or pressure sensors, yeah, you can supply. And then we've got HART communication, so we can take secondary parameters over and take those off. In terms of the cons, it's relatively high power. It's very slow, so HART, yeah, 1.2 kilobits per second. You've got limited ability to add extra parametric data, so you can't really tell too much about what's happening in the field. You get a sensor value, and that's about it. If you're lucky, you can get a secondary parameter on there. The output, it needs to be translated somewhere up here. So, you want to make use of it. You've got to go from 4 to 20 milliamps, work out, determine what the sensor's trying to tell you, and then act upon that data. And as I mentioned, the system wiring is very, very complex. Limited power distribution, and it's very costly in terms of the installation design. So to counter this, about 25 years ago or so, there was a move to Fieldbus technologies. So it's kind of simplified the middle bit here. Do away with the Martian cabinet. Running high-speed protocols here. Getting a bit better bandwidth from your sensors here. Bit of a more modern approach. But then you've got no single standard. So you're still looking at the problem that you create data here. It then has to go through a gateway. It has to be translated before you can really act upon that data. So in terms of the pros, well, the wiring costs are less. That's good. You've got a smaller cabinet footprint, which, if you've got space constraint, that's very good. It's a faster and easier installation process because it's getting towards plug and play, so that's great. You got high-speed parametric data, so you can take more information from the sensor and feed it back there. So that's good, and future expansion is really good. However, it is quite complex, and you have to have high-skilled field staff to install it and maintain it. The data rate's 31 kilobits per second. That's useful, but it's not great. There's no single standard, so there's no industry-wide interoperability. 4-20, it's used everywhere. They can be high-cost components for the Fieldbus, and you require gateways. That's the big thing here. So you create data, you translate it, you burn power, you add cost. Yeah, I'll move on from that. So the future, Ethernet to the sensor based upon 10Base-T1L, 802.3 CG. So just walking through the topology here, it's very simple. So from the controller, you'll be running across to a 10Base-T1L power switcher. That supplies the data onto the power line, sorry, the power onto the data lines even. Bring it across to a field switch, which again will be a multi-port switch. So taking in data and power and then distributing it to your sensor. So we create Ethernet packets here. We put them up into the field switch, and we switch them, and we take it back up onto the PLC, DCS, the controller, and then that sensor can go up to the cloud, and then you can act upon it. So from the moment it's created to the moment it's consumed, that data is in an Ethernet packet. So there's no translation, there's no delays, there's no additional cost, there's no additional power burned with these gateways, and it makes your network much simpler. And we've also got redundancy in here, because we're using ring topology. So T1L, Ethernet, 10 megabit, single twisted pair, power over data line, reusing the existing cabling. So you can run this 1 kilometer on a trunk, get close to your sensor, reusing the existing cabling. So that's the big, big benefit here. So 10 megabits, full duplex, 1 kilometer, twisted pair. Now the other benefit is being able to supply power to your sensor. So before we were talking maybe 30 milliwatts for 4-20 milliamp, a little bit more for Fieldbus technologies. Here we can go up to 60 watts. So 60 watt power in certain cases. If you're looking at intrinsic safety, 500 milliwatts. So in IS zone 0, you can supply that. And it's intrinsically safe by design. So from the conception, T1L was designed to be used in zone 0. So as I say, the benefits here, the cons, well, there's limited equipment availability today, i.e. there is no physical interface that's ready for production. We've got prototypes we're demonstrating. We can show the benefits there. It's a new network topology. And then integrating into brownfield, you've got a lot of sensors here that aren't going to be T1L ready for a long time. And these sensors that are, Fieldbus or 4-20 milliamps, you're not going to swap them out. So if you want to send an engineer to replace a sensor or an actuator, it's cost prohibitive. So we need some way to go from where we were to where we're going. So what we're talking about here is solutions for brownfield. So one solution is, a mixture between 10Base-T1L, so new sensors, new actuators, or somewhere where you need the performance. You would probably do the cost trade-off and replace the sensor actuator. But for the vast majority, you want to reuse your existing sensors. So you need to translate. So we do need a gateway of some form. Now, in the case of 4-20 milliamps, a remote I/O, yeah, that's good. You've got fixed function here, so you've got a combination of analog input, analog output, current, voltage mode, maybe some digital. But then specifying the requirements for your installation, everyone's going to be custom. So you need the ability to be able to swap out and mix and match, probably at a per channel basis. So the problem we're seeing is, moving to remote I/O with fixed function, you need to tailor each installation. And that gets expensive. It gets problematic because, you may have unused channels here. Or you may indeed run out of channels and have to add extra modules. And by default, you've got unused channels there, and it's becoming inefficient. You've got per module granularity, which I just mentioned there, and it's costly. So what can we do to make this process easier? So we've developed a technology called software configurable I/O. So on a per channel basis, we can configure this to be any function you want. So analog input, current voltage, analog output, current voltage, digital input, in the future, digital output. Both field and loop power as well on your currents. And that enables you to standardize or modularize your remote I/O, your field translation, your field gateway here. And therefore, you're going to get benefits of the cost there, in terms of the scalability there. So, what is software I/O? Well, as I just mentioned again, it's a way of making a gateway that you can configure in the field. So you can wire this thing up, and then post-wiring, post-installation, configure it via the control system. So that lowers your cost of installation. It lowers your cost of ownership completely. Extends the life of your field switches, especially if you want to upgrade your network here. The slight downside is that it will be a slight increase in cost per channel. But at the system level, your cost of ownership has actually reduced. So explain in a little bit more detail. Software I/O, let's say, any input, any output on any pin. So DAC, ADC, digital input, digital output, any function, any combination. It's basically I/O on demand. We've just released our first generation of the chips here. So we've got a 74412R, and that's intended for building control. And the 13R is for PLC DCS systems. Quad channel with HART compatibility. So what we're talking about is moving away from fixed function, multiple I/Os, where you may have 40, 50 different modules in your portfolio, and moving down to a more streamlined solution where you have one single module. So your cost of development, your cost of ownership, your cost of manufacturing is significantly reduced. So just wrapping up here. So the world is moving to Ethernet, and it's moving there very quickly. Installed sensors, it's not economical to swap those out. We need a solution for brownfield. We need to bridge from Ethernet to the legacy 4-20. Say it's going to be here for the next 20, 30 years. Fixed function I/O, it's not economical. It doesn't give you your best performance in terms of the cost. And by using software configurable I/O, we can have flexibility to give you exactly the I/O mix that you want in any installation. So further information, you can email me, analog.com, Industry 4.0. If you want to look at a T1L demo, we're in Hall 5, 129, and then some product pages as well here. Thank you very much.